So here's a video on 2.8. So this is about the derivative as a function. So what we're going to do is we're going to look at graphs of functions and then think about what the graph of the derivative looks like, because the derivative is a function. Of course, so if this is a graph of y equals f of x, then at each point, like if I choose a value of x, the corresponding value of y, if I trace it up to where the graph is, that y coordinate is f of x for that x coordinate. On the graph of the derivative, the graph, the way it should look is the y coordinate on the graph of the derivative should be the slope of the original graph. So for example, if I take a particular value of x, say this value of x, the tangent line would have a negative slope because I'm going down and to the right. So this is the original graph, but in the graph of the derivative, this value of x, since it has a negative slope, the graph of the derivative should have a negative y coordinate. So on the spots where this graph is decreasing, it's on its way down. So it's decreasing from here all the way up to -1, and then it looks like it's on its way back up. So when it's decreasing, it should have a negative derivative because that's a negative slope. When it's increasing, it should have a positive derivative. That's a positive slope. When it goes in between, like when it transitions between decreasing and then increasing, like at this point, it has, like if I were to draw the tangent line, it looks like it's horizontal. So that would be a 0 slope. So anyway, this is just an example where we have the graph of the original function, and then we're given 4 options for what the graph of the derivative could be. And try not to think too hard about these. This should be just a process of elimination, and only one of these answers should even make any sense at all. So what we're looking for is a graph that is negative, because this has a negative slope all the way up to x equals -1. And then our graph should be positive because this is increasing. This is a positive slope. And let me try to talk about a common misconception. Say down here, the part of the graph that's down here, this is below the x-axis. So these are negative y coordinates. Nevertheless, this is increasing. It's a negative y coordinate, but it's on its way up. So the derivative should be positive, even if the graph of the original function being below the x-axis, I would call this a negative y coordinate, but the derivative is positive. So basically, let's see if I can narrow it down to one answer just with this information. The derivative should be negative up to this value of x, and then positive up to this value of x, and then negative again because it's decreasing from this point on. So negative, positive, negative. That looks like C, right? When I say negative, I mean below the x-axis. So it's below the x-axis, and then positive meaning above the x-axis, and then negative again meaning below the x-axis. The others just do not fit that description. This one goes positive, negative, positive, negative. And keep in mind, I'm looking for something that goes negative because it's decreasing, and then positive because it's increasing, and then negative. This one goes positive, negative, positive, And then this one goes back and forth too many times. It's negative, positive, negative, positive. There's really only one that is negative, and then positive, and then negative again. So, yeah. Let's talk about a similar but slightly different one, and hopefully you can see this well enough. I have made an effort to draw, one of these graphs is in blue. That's this one, the one with two humps. It comes up like this, and then down, and then up, and then down. So that's the graph with Roman numeral 1. Then there's the red one with Roman numeral 2, and that's the graph that goes down, and then up, and then down. And then there's the black one, Roman numeral 3. It just goes up once and down once. So what we have here is a graph of an original function f and its derivative, and then the derivative of its derivative, which is f double prime. And I have to just identify which one's the original function, which one's f prime, and which one's f double prime. And I can do this using the same type of logic I used on the last example. I should be able to look at these graphs and say, okay, this one looks like it might be the derivative of that one. And then maybe if the third function that I see is the derivative of one of those, then I know everything I need to know. So let's start by just looking at one of these graphs. Maybe I'll look at the simplest one. I'm looking at Roman numeral 3 because that just goes up once and down once. What I notice about that is that it seems to be increasing until we reach this point, which looks like about x equals 0. So it's increasing and then decreasing. So it's the derivative of number 3. The derivative should just be positive and then negative. Do I see a function that is just positive and then negative? Meaning positive meaning above the x-axis, and then negative is below the x-axis. I mean, here's a function that's above the x-axis, but then it goes below the x-axis here. I would, if I'm looking for the derivative of 3, I'm looking for one that would go, it would be positive until x equals 0. This is not positive until x equals 0. It's positive until x equals whatever this is. So actually, I don't see the derivative of Roman numeral 3. And you know what that means? That probably means that Roman numeral 3 is f double prime. Because otherwise, if it was this, then I should see its derivative, because one of these is f prime, and if number 3 was this, then I would see its derivative, because its derivative is f double prime. The one whose derivative I don't expect to see is f double prime. The derivative of f double prime would be f triple prime, which is not shown. So it would make a lot of sense if number 3 was f double prime. But maybe I won't commit to that decision just yet. Let me look at another one. Like, say, I don't know, let me look at Roman numeral 1. Roman numeral 1, once again, it's this graph that has two humps. It goes up and then down and then up and then down. So what I should see when this is increasing, its derivative should be positive, so above the x-axis. So I would be looking for a graph that is above the x-axis from here all the way up to here. But then once we hit this point, this graph starts decreasing, so its derivative should be below the x-axis. And then it starts increasing again, so its derivative should be above the x-axis. And then this starts decreasing again, so its derivative should be below the x-axis. So let me ask you this. Do I see a function that is above the x-axis from here until here. It's above the x-axis until I reach this point, and then it's below the x-axis from here until here, and then it's above the x-axis from here until here, and then below the x-axis from this point on. And if you noticed, I just described exactly what the red graph does. It's the red graph is above the x-axis all the way. If I'm sweeping from left to right, the red graph is above the x-axis all the way up until this point, which is exactly when Roman numeral 1, the blue graph, that's exactly when this one stops increasing and starts decreasing, and that's when this one goes below the x-axis. So it's doing exactly what it's supposed to do. So it certainly appears that the derivative of 1 is 2. So now I think I have a guess for what the entire answer is, but I just want to check and think just a little bit. I was guessing that number 3 was the second derivative, and if 1 is the derivative of 2, or if the derivative of 1 is 2, then maybe 1 is f and 2 is f prime. Let's check something though. Actually, okay. I'm going to go ahead and fill in my guess. But I am going to check one last thing. We examined the graphs 1 and 2, and we decided, yes, it looks like the derivative of 1 is going to be 2. Let's look at the relationship between 2 and 3, because it should look like 2 and 3 have this same relationship. So once again, 2 is the red graph, 3 is the black graph. If I look at 2 and try to imagine what its derivative should look like, it's decreasing here, so that its derivative should be below the x-axis where it's decreasing. So where this is decreasing, and it's decreasing all the way up until this point, and it does look like the black graph is below the x-axis. Okay, so let's keep moving left to right. At that point, the red graph starts increasing, so the black graph, if it's the derivative, should be above the x-axis, which it is. And then at around this point, the red graph starts, it's on its way down again. So the black graph should be below the x-axis, which it is. So this, everything checks out, and so this should be our answer. Okay, so next example is about differentiability. So of course, right, we use the word differentiable to mean, can you take the derivative? And that may seem like a weird question, like why couldn't we? Well, I mean, the derivative it's defined as a limit. It's, do I have, yeah, I mean, it's one of these limits. The f prime of a is defined as this. So it's defined as a limit, and as we know, limits don't always exist. So there's a real question of, does the derivative exist, or is a function differentiable, or can you take the derivative? And in terms of graphs, what it looks like is that there are certain points where you can't take the derivative. And what do they look like? Any point of discontinuity would be non-differentiable. Any point of a vertical tangent line. Of course, the derivative is supposed to be the slope of the tangent line, but the slope of a vertical line is undefined. So if there's a vertical tangent line, it's not differentiable. Also, any graph with a corner, it's not differentiable at the corner. So the values of x for which this is not differentiable. So here's a point of discontinuity. So x equals -2 is not differentiable. This would be another type of discontinuity. This is a vertical asymptote. Of course, this is continuous from the right because there's a dot there, but that doesn't matter. If it's not continuous, period, then it's not differentiable. This, of course, I'm not a perfect artist, but what I tried to draw here is a vertical tangent line, in the sense that if you zoom in on this point, it looks like the graph is going straight up at this point. So this is my attempt to draw a graph with a vertical tangent line. So at x equals 1, this is non-differentiable. And then here we have just a corner. This is what I meant by a corner. And of course, this is a graph of a made-up function, but we know, for example, and this is not part of the example that I'm doing right now. I'm basically done with that. We got our answer, but I'm just illustrating. Here's an example of a real function that we're all familiar with, and it has a corner, right? The graph of y equals absolute value of x looks like this, and it has a corner at x equals 0. Yeah, so then the other thing we have to do for this section is to find a derivative of functions using the definition. So here's a function. Let me find the derivative. The derivative is called f prime of x. Here's the definition. It looks very familiar. In fact, I can just put a box around this. This is the definition of derivative. You can always just use this. But let me do it for this particular answer, or this particular function, because I have to do this example. Limit as h goes to 0, 3 plus 2 times x plus h minus 3 plus 2x over h. Yeah. I'm going to simplify this in a really easy way. 3 plus 2x plus 2h. And what does this look like? Again, whenever I'm doing a derivative, I'm doing a limit and h is going to 0 and I have h in the bottom. That means I always have to do algebra until I can cancel the h in the bottom. There's no easy way around that. What I see is some square roots and I see some subtraction, so this kind of, it's begging me to use the conjugate. Which would just be putting a plus in between. And let me use parentheses so I don't forget anything. Like that. And let me multiply this out. So I'm using the difference of two squares formula, so it's going to be this thing squared minus this thing squared, which is not scary at all, because when I do this thing squared, it just takes the square root off. And when I do this thing squared, it just takes the square root off. But I want to make sure to use lots of parentheses here so I remember to distribute this negative sign. On the bottom, I'm not going to multiply anything out. That is a common theme, if you've noticed, for what I do with the bottom. Like that. Now, everything on the top that does not have an h on it should go away. I see a 3 minus 3, I see 2x minus 2x, so yeah, I'm tempted to, oops, I kind of wrote h goes to infinity up there. H is going to 0. Right. So all that's left on the top is a 2h. So I'm like that. Cancel the h. And now that I've canceled the h out of the denominator, I should just be able to plug in h equals 0. And I can. This is 2 over... So this is the square root of 3 plus 2x. And then there's another square root of 3 plus 2x. So then I have 2 of them, but then I could cancel the 2 with that, so I would just get 1 over 3 plus 2x. And that's f prime of x. Okay, so then that should be about it for this video.